So I'm going to start with G over Q, a connected reductive group, and then I can associate to it a symmetric space, or really to the real points of this group, a symmetric space, which is a Riemannian manifold that has an action of G of R by isometries. And then also taking a sufficiently small, or to be precise, neat, compact open subgroup in the finite adelic points of the group, I can form a double quotient, which is a locally symmetric space for my group. This is xk, it's the double quotient of x cross G of AF. On one side, you quotient out by this compact open subgroup, and on the other side, you quotient out by the diagonal action of G of Q, where G of Q acts on X in the natural way, and then also on G of AF. And if you haven't seen this construction before, then don't worry about it. I'm just going to give you two examples that are going to illustrate the way in which these locally symmetric spaces can behave, and there's a fundamental dichotomy that will show up. So the first example is where your group is SL2 over the rational numbers, and then in that case, the associated symmetric space is hyperbolic 2 space, or which sort of can be identified with the upper half complex plane. And then the associated locally symmetric spaces, by strong approximation, they're really just quotients of the upper half plane by congruent subgroups contained inside SL2Z. They're going to be modular curves. And then another example that you should keep in mind is, say you try to increase the level of difficulty and you go to the restriction of scalars of SL2 from some imaginary quadratic field to down to Q. So in other words, you sort of want to think about SL2 over some extension of Q, such as an imaginary quadratic field. So in that case, the corresponding symmetric space is hyperbolic 3 space, and the corresponding locally symmetric spaces are also going to be quotients of hyperbolic 3 space by certain arithmetic groups. And so the locally symmetric spaces are going to be arithmetic hyperbolic 3 manifolds. So these are two examples of locally symmetric spaces that you can obtain that behave in a fundamentally different way. So in the case of SL2 over Q, the symmetric space has a complex structure, and that descends to the quotients, and the modular curves are Riemann surfaces. And in fact, more is true in this case, because modular curves are really algebraic curves that are defined over Q, or possibly over some finite extension of Q. And so they really have this sort of number theoretic structure as well. And then this example can be generalized to higher dimensions and to higher rank groups, but not in sort of in an obvious way. But the general case also corresponds. So there is a generalization where the locally symmetric spaces are algebraic varieties defined over number fields, and that is the case of Shimura varieties. And so, for example, that is the case where the group that you start with is a symplectic group, say GSP2n for any integer n. And another example of a group that will give rise to locally symmetric spaces that have an algebraic structure is the case of unitary groups. Okay, so that's one phenomenon. And then in the second instance, you can see that the symmetric space has odd real dimension, and so the locally symmetric spaces do as well, and so they have no hope of having even a complex structure. So there's definitely not going to be the structure of algebraic varieties in that case. And so if you want to understand the group GLN, or maybe even say the restriction of scalars of GLN, from F to Q, where F is an arbitrary number field, then it turns out that this general case behaves kind of like this case of SL2 over an imaginary quadratic field. So in general, these locally symmetric spaces do not have the structure of algebraic varieties. They are just real manifolds, I mean, equipped with a lot of symmetry, but just real manifolds. All right, and from now on, I'm going to focus on this second case. So I'm going to set my group G to be this restriction of scalars, and for the time being, I can allow F to be an arbitrary number field. Okay, and I need to just introduce some notation because I want to talk about the cohomology of these spaces, but I want to allow myself to have twisted coefficients. So I'm going to take E over QP to be a finite extension, O the ring of integers, pi a uniformizer in O, and then F the residue field. And then I want to take, I want to consider some irreducible algebraic representation of my original group over E that is described by some highest weight vector. And let me assume that my field of coefficients is large enough so that the group splits over that field of coefficients. And then I have some vector lambda, which to be precise is an element of this, like this many copies of Z to the n, indexed by the embeddings of F, say into QP bar. And such a highest weight vector, I mean, there are also some inequalities. Such a highest weight vector is going to determine an irreducible algebraic representation. And inside of it, I can consider an O lattice, which is stable under the KP. So I have my adelic subgroup K, and I want to just consider the component at P. So I want to consider a KP stable O lattice inside my original representation. There's something, say the dual Weil module is a standard choice. So whenever I have something like this, because of the definition of the locally symmetric space by taking a double quotient, you can use this representation of KP to get essentially a KP equivariant sheaf upstairs before you take the quotient by K, and then that will descend to a sheaf downstairs on the locally symmetric space, which I will denote by nu lambda. So this is going to be a local system of O modules on my locally symmetric space. And what's really important is that it's just sort of, it's an integral object. So I'm not taking rational coefficients, I'm taking integral coefficients. And then the object that I'm really interested in is the cohomology of the locally symmetric space with these twisted coefficients. And I want to consider cohomology in some arbitrary degree I. And either, say, it's always going to be the singular or the Betti cohomology. And I can take either usual cohomology or compactly supported. Ultimately, I want to understand both. Okay, so that's the object that I want to understand. And when people talk about torsion in the cohomology of locally symmetric spaces, what they really mean is they want to understand this kind of cohomology, say with integral coefficients. And this is not just a vector space, but it has an action of a spherical Hecke algebra that is obtained by taking a restricted product of Hecke algebras at all but finitely many good primes. So I won't go into the definition of that, but I just want to say that there is a large commutative algebra that acts on the locally symmetric spaces xk by correspondences, that also acts on these twisted coefficients, and therefore you really get an action of the Hecke algebra on the cohomology. And ultimately what you're interested in understanding are systems of eigenvalues for this Hecke algebra that can occur in these cohomology groups. So I'm going to denote by star any sort of this object together with the Hecke action. And what I want to say about it is that if you invert P, then this cohomology can be described in terms of automorphic representations of GLN of the adels of the number field F. And this follows from work of Franke and also Matsushima. I guess goes back to Matsushima in the case where, say, if your locally symmetric space was compact. But the reason people talk about torsion in the cohomology of these locally symmetric spaces is that, if you really want to understand this object, well, it turns out that you actually lose information when you invert P. So this can contain torsion. It can contain a lot of torsion in some instances. And there are quite a few results available these days, for instance, due to Bergeron and Venkatesh, I think show that this grows exponentially with the index of the level in the case, say, where F is an imaginary quadratic field. Okay, so this is what we're interested in. And why do we care about it? Well, one big reason to care about it is that Caligari and Garrity in 2011 found a way to extend the Taylor-Wiles method to the setting of basically locally symmetric spaces over arbitrary number fields. So the Taylor-Wiles method is used to prove modularity lifting theorems. So it's used to establish sort of a link between Galois representations and automorphic forms. And sort of at least in some setting, at least say this cohomology of this locally symmetric space after you invert P, you can see that it does give rise to automorphic representations of GLN of AF. So it makes sense to ask about, say, whether you can connect Galois representations to systems of eigenvalues that occur in here. And so the Taylor-Wiles method was originally implemented in the setting of modular curves, which is a setting where you do have this kind of algebraic structure. And one could conceive how to generalize it to some higher dimensional cases, but so most of the results were for definite unitary groups. And then you could also imagine in some settings implementing it for more general Shimura varieties. But there was a genuine obstruction to making the method work in more generality. And I'm going to explain later on roughly where this obstruction comes from. But I just want to say that Caligari and Garrity really had a breakthrough where they figured out how to extend the Taylor-Wiles method to really apply to general locally symmetric spaces and to apply beyond the setting of Shimura varieties. And however, what they outlined was conditional on three conjectures. And these three conjectures have to do with understanding these integral cohomology groups in a lot of detail. And I'm going to say more about this in a second, but just to say, so that's why we care about understanding these, because we can hope, say, to implement the Taylor-Wiles method in this more general setting using the program outlined by Caligari and Garrity, and therefore we can hope to extend the Langlands correspondence in this more general setting. And there are already some unconditional results. And so the one that I want to mention was in fact a result that was obtained at the IAS. And that is this 10-author paper. So it's due to Patrick Allen, Frank Caligari, myself, Toby G, David Helm, Bao Lehung, James Newton, Peter Scholze, Richard Taylor, and Jack Thorne. And this was, the paper was finished in 2018. And what we were able to do was to start out not with a general number field, but rather with a CM field, and then take, say, an elliptic curve over the CM field, which is a non-CM elliptic curve. And so that's the general case, an elliptic curve that doesn't admit complex multiplication. And then we were able to implement the Caligari-Garrity method in arbitrary dimensions, and we were able to prove as a result that the elliptic curve is potentially automorphic. So up to going to some bigger CM field, it is attached to some automorphic representation of GLN over that CM field. And moreover, even sort of the arbitrary symmetric powers of this elliptic curve are potentially automorphic. And that in turn gives you this equidistribution result that is the Sato-Tate conjecture for that elliptic curve. So that's a concrete application of understanding torsion in the cohomology of locally symmetric spaces. And I should say what I'm going to discuss from now on is always going to be about the Betti cohomology of these locally symmetric spaces. And Caligari and Garrity also have a version of their method that applies to the coherent cohomology of Shimura varieties. And that has also been implemented unconditionally. That's in a recent paper of Boxer, also in 2018, Boxer, Caligari, G, and Piloni. So this is sort of a parallel story, so I won't say more about it, just that they were able to reprove this result about elliptic curves, and in fact, they were able to prove that abelian surfaces over the rationals are potentially automorphic. All right, so this is sort of the introduction slash motivation. Are there any questions so far? All right, so the next thing I'd like to say is that, well, the Caligari-Garrity method relies on 3 conjectures, and I want to be precise about what these conjectures are. So the first one is on existence of Galois representations. So if you want to implement sort of a modularity lifting, which amounts to showing that a Galois representation is automorphic, then, well, you first need to have the direction from automorphic to Galois. And so this is what existence of Galois representations is about. It's about sort of first establishing the direction from automorphic to Galois. For instance, in the original case of modular curves, it's about associating Galois representations to modular forms. One subtlety that Caligari and Garrity noticed was, in some sense, to make things work in this higher dimensional setting, your notion of an automorphic form needs to be enlarged. So it's not enough to just consider these characteristic 0 automorphic representations of GLN of AF, but you really have to consider the integral cohomology. All right, so I'm going to take TK lambda to be just the faithful quotient of the Hecke algebra that acts on the cohomology of the locally symmetric space with integral coefficients. And K is going to record the level, lambda is going to record the weight. And maybe also if you want a particular degree, you can also keep track of, say, if I put here I, you could keep track of TK lambda I. So I want to take a maximal ideal of this faithful quotient. This is amounts to saying I want to pick out a mod P system of Hecke eigenvalues that occurs in one of these cohomology groups. And then what the direction automorphic to Galois would suggest is that there should exist a global Galois representation, so of the absolute Galois group of F, that is valued in GLN of, say, F bar, which is continuous, semi-simple, and which is associated to M in a precise sense. And that precise sense is that at all but finitely many good primes, you want the Satake parameters that you can read off from this maximal ideal to match the Frobenius eigenvalues of the residual Galois representation. And because the representation is semi-simple, by Chebotarev, that completely determines it. Okay, and so one thing to notice is that when you start out with a system of Hecke eigenvalues that is really torsion, this Galois representation I mean, you know, you're saying more than what Langland's reciprocity predicts, right? So this predicts that this should extend even for torsion classes. And then there's something even stronger that you can say. So assume that the representation is irreducible. Maybe it's just terminology, but people say M is non-Eisenstein. Then you expect even more, not just that you have a residual representation, but in fact that you have a lift of this residual representation to some representation that really sees sort of the entire or completion of the Hecke algebra at this maximal ideal. So it's not just the residual representation, but really a whole family of Galois representations that are associated to everything that you see on the automorphic side. So you expect that there is a global Galois representation valued in GLN of the completion of the Hecke algebra at M, which lifts the residual one, which is continuous. In fact, it's going to be irreducible. And it also satisfies some version of this compatibility at all but finitely many good primes, where you can really specify the characteristic polynomial of Frobenius in terms of Hecke operators and some generalization of the Eichler-Shimura relation. All right, so this is the conjecture, and in this generality, it's extremely strong because I have just assumed that F is a number field. But now, so if you allow F to be a CM field, by which I mean either a totally real field or an imaginary quadratic extension of a totally real field, then this is the existence of Galois representations is essentially a theorem that is due to Schulze. And I should say this builds on work of Harris, Land, Taylor, and Thorne in characteristic zero. And there's a slight detail also that this Galois representation is not really valued in the Hecke algebra, but only in the quotient of the Hecke algebra by some nilpotent ideal of bounded nilpotence degree. This is something that I'm pretty much going to ignore from now on. It is important for some sort of subtle questions, for instance, to do with, say, the Bloch-Kato conjecture. But for just proving modularity lifting, you only need to understand supports of Hecke modules. And so the nilpotent ideal doesn't make a difference. Okay, so this is the first conjecture, and essentially Schulze proved in 2013 what one needed to implement the Caligari-Garrity method. The second conjecture is local global compatibility. And I guess this is really what I'm going to spend a big part of my talk on. So first, I'm just going to phrase it a little bit vaguely. So I'm going to say, let V dividing L be some prime of our number field. And in fact, at this point, because this is the only setting where we have Galois representations, let me assume that F is really a CM field. And so let's take some prime V of that CM field, and let's assume that it lies above a rational prime L. Then what local global compatibility would say, roughly, is that you expect that the level of your automorphic form or torsion class at V would determine the ramification in the restriction of the Galois representation to the decomposition group at V. And when V is a prime above P, then you need to introduce, you need to keep track of more information, not just the level, but also the weight. So the weight is encoded in this highest weight lambda V. So in general, you expect something like this, that the weight and the level determine the ramification locally. In characteristic zero, you can formulate something really precise by saying that you know, especially because you're doing GLN, you just expect a compatibility with the known local Langlands correspondence for GLN. When you allow yourself to work integrally, it's a little bit subtle to actually formulate local global compatibility precisely. But let me say, so this is roughly what you expect. And then when L is a prime that's different from P, then the problem is somewhat more accessible. So in characteristic 0, this is already a theorem of Varma. So she proves it for these Galois representations constructed by Harris, Land, Taylor, and Thorne. And then when you work integrally, at least when you allow yourself something like Iwahori level, so not too ramified, this is done in the 10-author paper, and more generally, it's probably approachable using Helm's theory of the integral Bernstein center. And so in all the instances when L is not P, the strategy is essentially to look at Schulze's construction of Galois representations and redo that construction by keeping track of extra Heck operators at these primes, so at the prime V, where you have ramification. Okay, and then you have the instance where the prime L is actually equal to P. And I want to say that this is slightly, this is more tricky than the other case. And the first reason why you might think that it's tricky is because you cannot use Schulze's construction. So you cannot try and follow that construction and prove local global compatibility above P. The reason is that his construction goes via some perfectoid Shimura varieties where you really have to consider sort of infinite level at P. So the construction is via congruences, and at some point you go to infinite level at P. And so you lose track of the level at P, which is this piece of information, and you also lose track of the weight because, say, if you're working mod P to the n and you increase your level at P, that also allows you to construct congruences to other weights. So the kind of information that you would expect to determine the ramification is lost in the construction. So that's one reason. And another reason why this is slightly more subtle is that it's a bit hard to formulate what the question is, in the sense that you need the right notion in integral p-adic Hodge theory. So away from P, if, say, the level was GLN of OFV, so you had level that was sort of didn't see this prime, then you would just expect your representation. And in fact, it's true that the representation is unramified. But at P, sort of even in characteristic 0, the best possible thing you can hope for is this notion of crystalline. And that's a notion that's very hard to make precise integrally. Although recently there's been a lot of development in integral p-adic Hodge theory. But so that's one reason why, another reason why this case is a little bit subtle. And so there is a paper of G and Newton where they do formulate a conjecture, a precise conjecture for what this local global compatibility result would be above P. And this uses Kissin's crystalline deformation rings. So Kissin constructed some quotients of the unrestricted local deformation ring at P that on the generic fiber see all the crystalline points. And then the quotient is really constructed by taking the Zariski closure of what you have on the generic fiber. So somehow it's the right notion on generic fiber and then defined by taking closure. But still, you can be optimistic and conjecture that this crystalline deformation ring that sort of sees the Galois representations that you're constructing. And so to be precise, the global representation, rho m, this universal family of Galois representations, gives you a map from the universal global deformation ring to the Heck algebra, or the Heck algebra mod I, because that's what we have. So this map is given to you by rho m. Then you have, just by restricting from the global representation to something local, you have a map. So you have a map from the unrestricted local deformation ring. Now here you have Kissin's quotient, so that sees in characteristic 0, the points that are crystalline and have Hodge-Tate weights determined by the weight of the automorphic representation. And so the conjecture is that this map, in fact, factors this way. So factors through Kissin's quotient. And that's something that you can formulate precisely, but still it's a little bit not obvious how to prove it, because the whole construction of this map, again, goes via congruences mod p to the n, and then this ring is defined by taking closure from what you see after inverting p. So there's some incompatibility here that makes it a little bit tricky to see right away how to prove that something like this could happen, even if you had a new construction of the rho m. And of course, in the 10-author paper, where we prove this result for elliptic curves, we do implement, so we are able to prove some cases of local global compatibility, but the cases that we prove are really restricted. So essentially we prove the two cases where you can actually formulate the conjecture differently, where you have the right notions in integral p-adic Hodge theory. So, I mean, basically we prove the Fontaine-Lafay case, and that's essentially where the weight is small with respect to the prime p. And then there's also an ordinary case where, for instance, you see things at Iwahori level that occur in the ordinary part of cohomology in the sense of Hida, and then you expect the Galois representation to be upper triangular, and you expect some relationship between, say, UP eigenvalue and Frobenius eigenvalue. Those are both settings where you can keep track of the right condition integrally. But for arbitrary weight lambda, or in the Fontaine-Lafay case, I guess you also need P to be unramified in F. So when P is very ramified in F, again, arbitrary weight lambda, P ramified in F, these methods won't work. All right. So I guess this is what I wanted to say about the local global compatibility. And so these are two of the three conjectures that Caligari and Garrity need. And these two also occur in the Taylor-Wiles method. So when you try and prove a modularity lifting theorem, you need first the direction from automorphic to Galois, which gives you a map from a universal deformation, Galois deformation ring to a Hecke algebra. And then you need to control it via local global compatibility to say that it factors through the right deformation ring. And then you can hope and say that maybe after taking reduced quotients, you can identify the deformation ring in the Hecke algebra. So these are things that you would expect. I guess the thing that's new is that you sort of in your automorphic, on the automorphic side, you incorporate torsion. But otherwise, it's what you see in the Taylor-Wiles method. And the third conjecture that they need is the one that's really sort of captures the subtlety of what happens when you go beyond the Shimura variety setting and really consider the case of general locally symmetric spaces. And so I want to discuss that a little bit as well before I go to say what's new about local global compatibility. So in order to formulate this third conjecture, I need to define some invariants. And so let me just recall the definition of the symmetric space. This is, you look at G of R, and you take a quotient by a maximal compact, and if the group is semi-simple, then that's all you need to do. And if not, then there's also some torus part, which is this A infinity. So you can define two invariants. One is L0, which is the rank of G of R, thought of as a real Lie group, minus the rank of K infinity, minus the rank of this torus part A infinity. When you have a Shimura variety, this invariant is always equal to 0. In general, it's computable, and for GLN over F, it's never going to just be 0, or for general N. And then you also have Q naught, which is just chosen roughly so that you have a range of degrees, Q naught to Q naught plus L naught, that is symmetric about the sort of dimension, middle dimension of cohomology for this X. So Q naught is half the real dimension of X minus this L0. The cohomology of X is concentrated in degrees 0 to dimension of X. And then this is a range of degrees that's smaller than that, but that is symmetric about the middle. For example, when you have SL2 over Q, so that's a case where you have this algebraic structure, that's the case of modular curves. In that case, this L0 is equal to 0 and Q0 is 1. And that's saying the range of degrees that you're looking at is just H1 of the modular curve. And by the Eichler-Shimura isomorphism, we know that that's the interesting degree of cohomology for the modular curve. That's the one where you see cusp forms contributing. When you have this restriction of scalars from an imaginary quadratic field to Q of SL2, then suddenly you see L0 equals 1 and also Q0 equals 1. So this is the case of arithmetic hyperbolic 3 manifolds. You have cohomology in degrees 0, 1, 2, and 3, but the range of degrees that you're looking here is just degree 1 and 2. Okay, so I've sort of defined now for each locally symmetric space a range of cohomology degrees that we should be looking at. And now we want to assume that the residual representation is irreducible, really absolutely irreducible. Then what you expect is that after localizing at a non-Eisenstein maximal ideal, so after localizing at something for which the Galois representation is irreducible, you do not see the cohomology in the full range of degrees, but rather the cohomology is just concentrated in this restricted range of degrees that is symmetric about the middle and that has length L0. This is a conjecture that's maybe a folklore conjecture. It's certainly stated in this Caligari-Garrity paper. It's also mentioned in Emerton's ICM talk. So I'm not sure exactly who to attribute it to, but so this conjecture is crucial for implementing the Caligari-Garrity method. In some sense, allowing torsion here in the sort of existence of Galois representation, considering torsion in addition to characteristic zero automorphic forms, makes you have enough things on the automorphic side to be able to sort of hope that you can prove your modularity lifting. And then this conjecture, sorry, and then, I'm so sorry. The conjecture about vanishing of cohomology cuts down. So that's sort of saying that you don't have too many automorphic forms. So you want to get it precisely right so that you can hope to match it with what you see on the Galois side. So why might you think this is a reasonable conjecture? Well, one thing is that it's okay in characteristic zero. So for instance, for GLN over F, you can prove it using work of Franke, and then ultimately it reduces to a computation of Borel and Wallach about the GK cohomology of tempered representations. So if you invert P, then this is something that these days we can prove. Oh, and I guess it uses this, but it also uses, even just formulating it, uses the existence of Galois representation. So I guess it's okay as long as you have the Galois representation. There's also been some recent progress in the case of Shimura varieties, which is sort of implies this is the case where L0 is equal to 0. So very special case, but recently there's been quite a bit of progress on understanding this conjecture for Shimura varieties, but with integral coefficients, not just characteristic 0. And then also you can prove it in some low dimensional cases. So for instance, you can prove it by hand for arithmetic hyperbolic 3 manifolds, because you essentially have to show that the cohomology that you see in degrees 0 and 3 is Eisenstein, and you can understand those degrees essentially by class field theory. Okay, and then the final thing to say is that there was another great insight of this time of Kara and Thorne. They noticed that when you want to apply the Caligari-Garrity method to prove some sort of modularity lifting result, but you already have an automorphic point in characteristic 0, not just a torsion class, then in fact, it's enough to know this vanishing conjecture in characteristic 0. So this result that I said is okay. Right, so sort of in general, we would want to know this kind of vanishing with integral coefficients. But for some applications, for instance, for these applications to potential modularity, it's enough to know the vanishing after inverting P. Okay, so this is somehow, yeah, this IAS workshop. We essentially, the first part, the first conjecture was known due to Scholze. The second conjecture, we figured out how to prove in some special cases. And then finally, we figured out how to sidestep the third conjecture and make it compatible with the kinds of arguments that go into proving these potential automorphy results or non-minimal modularity lifting. And I think this is all I'm really going to say about this vanishing of cohomology and this generality. And for the remaining part of my talk, I want to just focus on local global compatibility results. But before I do that, are there any sort of questions about what I've said so far?
Why do you need why do you need the irreducibility of the Galois representation to get it to work for characteristic 0?
Why do you need the irreducibility of the Galois representation to get this result in characteristic 0? Is that the question?
Yes, that's the question.
Well, I think you can show, for instance, that if you try to look at arithmetic hyperbolic 3 manifolds and you just try to understand what H0 is, there you're going to see a representation that is a sum of characters. So certainly if you don't put any sort of condition on the representation, you cannot hope for the cohomology to vanish. And then
I see what
you
you're
want
saying.
to,
okay, great.
yeah.
Perhaps you could say a word about the cases where you prove in this 10-author paper, or maybe the other people did in the other paper, Ramanujan, where you don't invoke delete. So you do all the symmetric powers. Can you say a word about that and how general that is?
I can say a word about this, yes. Okay, and that's a great question, and it's the right time to talk about this. Okay, so, right, so this is done in the 10-author paper. I sort of wanted to keep, sort of not mention it too much, and so I chose one of the results that we prove in this paper. The other result that we prove in this paper is towards the Ramanujan-Peterson conjecture. So that is for an automorphic representation of GL2 of AF, but there's a very important, and F now is a CM field, but there's a very important restriction, namely, it has to be, depending on your normalization, say parallel weight 2, or say trivial weight. So something that contributes to the cohomology of the locally symmetric space, not with coefficients, twisted coefficients, but really with constant coefficients. So in that case, we are able to prove the Ramanujan conjecture for yeah, I guess a cuspidal automorphic representation of GLN of AF, where F is a CM field, and it has trivial weight. And so the way that we do it is via proving potential automorphy of the symmetric powers of the Galois representation associated to this automorphic representation. So it's the same technique as we use for E. But really the key thing is somehow we prove a potential automorphy result for symmetric powers of Galois representations that have Hodge-Tate weights 0, 1. So or maybe that's something that happens both in the case of the elliptic curve and in the case of this representation. So the weight is restricted, the Hodge numbers that you see on the Galois representation. And one could hope, so ideally you want to prove it, say the next thing that you want to do is you want to try and prove arbitrary weight. So instead of parallel weight 2, say weight k. Then the issue is that I think to prove the potential automorphy result that you want, you need to prove some kind of change of weight result. So instead of proving just a modularity lifting theorem that keeps your weight constant, you want to prove some kind of modularity lifting where you also allow, say you construct some congruence to some weight where you have more flexibility in what that weight is. And that's something that we don't know how to do at the moment. I mean, in some sense, what I'm going to talk about will have an application to that, because, you know, if you want to allow arbitrary weight, you also need this conjecture on local global compatibility even to get started. And so the first step will be to prove the local global compatibility in arbitrary weight. So this would be for some weight, like arbitrary weight lambda. But even beyond that, there is a result for definite unitary groups that is due to Barnett, Lamb, G, Garrity, and Taylor that maybe is not clear how to prove it in this setting. But I think Scholze and Hellman and Scholze have some ideas for how to do this if they are given the local global compatibility input. But they're not quite, or like at least last time I checked, they weren't quite there yet. So I don't think it's hopeless, but yeah. Other questions? All right, so what do I want to say about local global compatibility? The starting point is the following theorem that is joint work of myself and Scholze, and this was sort of finished in 2019. So in some sense, this 10-author paper relies on this theorem that we completed a little bit later. But now that it's available on the archive, I don't want to waste too much time on stating it precisely. So I'm just going to give you sort of a rough statement of it. I'm going to take some unitary Shimura variety that is attached to a unitary group that is quasi-split. And this unitary group should essentially be obtained by restriction of scalars from an imaginary CM field F to the maximal total real field subfield F plus, but of course to have a Shimura variety, you want to view it as a group over Q. So this is going to be a non-compact unitary Shimura variety. And then you want to take a system of Hecke eigenvalues that occurs in the cohomology of this non-compact Shimura varieties, and that satisfies a genericity condition at an auxiliary prime that is not P. So some arbitrary auxiliary prime. This would be sort of a finite analog of this temperedness condition that occurs in the theorem of Borel and Wallach. Except, so there's some genericity condition like this, and then there's also a condition that the associated Galois representation to this M tilde is not necessarily absolutely irreducible, but at least has length no more than 2. And then if you have sort of this global condition and this local genericity condition, you can show that the cohomology of the Shimura variety with compact support and with arbitrary twisted coefficients that are mod P, after localization at such an M tilde, compact support cohomology is just in the middle degree and below. And after localization is such an M tilde, usual cohomology is just in the middle degree and above. So there is sort of this kind of splitting up of the two kinds of cohomology. And this is something that holds mod P, and it's an exercise to show that from this theorem, you get this corollary. So there's a Hecke equivariant diagram.
Sorry? Should those equations say HI is not equal to 0?
Yes. Thank you, yes. They should say not equal. Yes, not equal, but rather, yes. Okay, so it's an exercise to get the following thing. If you look at cohomology really in the middle degree, and this time with integral coefficients, and you localize at such a maximal ideal, then it turns out the cohomology, the usual cohomology of the Shimura variety, surjects onto the cohomology of the boundary of the Borel-Serre compactification. And at the same time, this usual cohomology is torsion-free, so injects into the space that you get after inverting P. So this part is torsion-free. On this side, there can be torsion, but you know that anything that you see here will lift to this and then embed in the characteristic zero space. And once you're in characteristic zero, proving the local global compatibility result is more like you can hope to do it. There's some tricks involved, but you have a lot more techniques available to you, and so you can essentially do it. And so the key idea is that you start out with some level and some weight and some cohomological degree and some system of eigenvalues on the side of the locally symmetric space for GLN F. And then you show that you can choose some level on the Shimura variety, K tilde, some weight on the Shimura variety, lambda tilde, and then you're determined some system of eigenvalues, M tilde, such that the ith cohomology on the level of the locally symmetric space contributes to the left-hand side of this diagram. And then by chasing the diagram, you can understand it. So this is the basic idea for how you use this theorem to prove a local global compatibility result that L equals P. And this is tricky because on the side of the locally symmetric space for GLN, you have an arbitrary degree I that is anything in the range from 0 to d-1. And on the other hand, here, you're really forced to be in the middle degree. And so the argument is quite tricky and involves various congruences, and you always have to sort of do some induction and change your lambda tilde. So maybe it's a little bit imprecise in the sense that maybe you need a bunch of these rather than just one. And the whole process we call degree shifting in this 10-author paper, and we implement it in the Fontaine-Lefay and in the ordinary case. Okay, so this is now what we can prove using a new idea. So this is joint work in progress of myself and James Newton. And because this is in progress, I do want to tell you what conditions we expect we will have precisely, right? It's not available, so I can't send you just to look it up. So I want to start with some imaginary quadratic field that is a composition of a totally real field and, an imaginary CM field that's a composition of a totally real field and an imaginary quadratic field. And I want to assume that my prime P splits in the imaginary quadratic field. And then I want to choose a place of F plus above this prime P. Okay, and so I want to prove local global compatibility in the crystalline case. To do that, I have to assume that my level is full at this V. So it's GLN of OFV for the two primes above V bar in F. So both V and V conjugate need to satisfy this. There's an inequality that needs to be satisfied, and that's because essentially I want to keep my V bar fixed, and I want to use the other primes above P as auxiliary primes. And there's some inequality that we're forced to have to say that you have enough auxiliary primes to allow yourself to go to all degrees. And then there's the condition that this representation is absolutely irreducible and is generic, this kind of local condition at some other auxiliary prime or maybe just some large image condition. This is needed so that you can apply the first theorem. And then the claim is, so under these conditions, but for arbitrary lambda, for arbitrary prime p, for arbitrary ramification of p and f plus, this diagram factors as you expected it to factor. And so, you know, this can give you a more precise local global compatibility statement in characteristic 0. It's also the kind of result that it sounds technical, but in fact, it will allow us to generalize the automorphy lifting theorems in the 10 author paper to this crystalline case. And it factors as desired, but up to possibly enlarging this nilpotent ideal. So we certainly don't know how to do it without a nilpotent ideal at the moment. And so maybe just a word about what the key idea for proving this is. The idea is to sort of use somehow Hida theory, but in the more representation theoretic formulation of Emerton. And so basically you choose P to be the Siegel parabolic inside the big unitary group. And that's going to be the one that has our GLN over F as a levy. And then you want to consider a version of this diagram where at the prime V, you do not just have cohomology at finite level, but you really have P ordinary completed cohomology. And you want to implement basically P ordinary degree shifting at this prime and some strengthened version of the Fontaine-Lafay degree shifting at the auxiliary primes. And what this buys you is that, well, you're trying to understand rho m by first sort of an n-dimensional representation by first looking at the 2 n-dimensional sum of rho m plus its conjugate dual. And you want to construct a congruence between this and some global Galois representation that you understand. And now the problem is if you could really construct a characteristic 0 lift of rho m that you knew was crystalline with weight determined by lambda, then you would be in business by a theorem of Tongvu. The problem is you cannot guarantee that there is a global lift like this. But what this P ordinary parts idea does is it allows you to construct a congruence between something like this and some global representation, which at least after you restrict to the decomposition group at the prime that you're interested in, looks block-up or triangular. And so once you have that, you don't have a global lift of rho m, but you do have a global, sort of a lift of rho m restricted to GFV, a characteristic 0 lift of rho m restricted to GFV. That is crystalline and where you can keep track of the Hodge-Tate weights. And then you can apply this theorem of Tongvu. All right, and this is a bit sketchy because you need to actually work with determinants rather than representations, so pseudo representations. But anyway, this is the key new idea. And some remarks to end is that the method, there's some technical things that we need to implement, but we expect that the method should generalize to cover potentially semi-stable representations, not just crystalline ones, except that you will never be able to really, with this method, really identify the monodromy operator. But up to that, you should be able to, say, understand the Weil representation of the Weil group. The really bad thing about this theorem is that condition 3 excludes the case of imaginary quadratic fields. So for imaginary quadratic fields, you only have one prime above P. There's no auxiliary primes. And that's bad because in the Caligari-Garrity method is much more flexible when you know this vanishing of cohomology for integral coefficients. And that we only know for really in very special cases, such as for imaginary quadratic fields. And finally, the other good thing is that this result will allow us to generalize the automorphy lifting theorems in the 10-author paper. Okay, so this is all I had to say. So I'll answer any questions now.
Thank you. So if you have a question or comment, please unmute yourself and ask Anna.
Which automorphy lifting theorems are going to be generalized for GLN or what?
Yeah, it should be in the case of GLN. So there's no, so this sort of minimal automorphy lifting theorem should be fine. And then there's also, I guess, the non-minimal one that incorporates Taylor's Ihara avoidance trick.
But this means only for totally real fields, GLN over totally real fields. You can't.
CM fields.
For CM.
So imaginary.
Oh, but not not imaginary quadratic. Or that's the only one that's missing.
Yeah, somehow imaginary quadratic. I mean, okay, so if you give me a field, I won't be able to exactly prove it. So you need these conditions.
Right.
But in some settings, if you say are trying to, like, depending on what kind of result you want to prove, you can't, if you're allowed to use base change, if you're in characteristic 0 and you're allowed to use base change, essentially you can always put yourself in a situation where these conditions will be satisfied. Which is why I said that this should be applicable to, trying to prove more general cases of Ramanujan. It should also be applicable to questions about actual modularity of elliptic curves over imaginary CM fields.
Should also give new cases of irreducibility of Galois representations.
I don't have that in my head enough to be able to tell you whether that's true or not.
You will, though, I think.
Any other question?
Maybe you can say a word about something to someone like me who only understands the analysis, or if I do understand it. But the vanishing theorems that you quoted of Matsushima or Borel-Wallach involve unitarity and integration by parts. Am I correct? And in this p-adic world, you have some vanishing theorems. So my question is, what tool, say in your work with Schulze, is used to get the vanishing? I didn't quite get that. What's the mechanism to get the vanishing?
Okay. So basically, the first thing that we use is a p-adic period morphism that is an analog of, say, the Borel embedding. So if you look at the symmetric space, embedding that into the flag variety over the complex numbers. So there's a p-adic analog of this that will take, this Borel embedding is sort of taking on the upper half plane, say you have the Hodge structure of the elliptic curve and you just remember the Hodge filtration. There's a p-adic version of this. So that's the first thing. Then we analyze the p-adic geometry of this, the geometry of this p-adic period morphism. And one thing that is crucial is that there's a perverse sheaf that shows up. So somehow the map to the period morphism is in some sense both affine and proper, and so preserves perversity. And so perverse sheaves will give you essentially these inequalities. Except, so we also have a stratification on this Hodge-Tate period domain, so the target of the p-adic period morphism. And this stratification essentially knows about the shape of the representation at P. And so sort of the innermost stratum will see things that are supercuspidal. And then, as you go, like the closed stratum, which is the ordinary one, will essentially see the principal series one. So this genericity condition allows you to eliminate genericity plus vanishing plus an induction argument, so genericity plus perversity plus induction, allows you to eliminate Newton strata one by one up until you get to the closed one, which is the ordinary one, and that's zero dimensional.
Okay.
And there is a trace formula computation that, yeah, like somehow, yeah, that is key.
Okay.
Any other question?
So how far away are you from getting like full R equals T theorems for the representations that you're considering? And furthermore, if you want to get non-minimal ones, how much further is that?
I'm not sure what you mean by full R equals T, because like for one thing, you have this nilpotent ideal. And so I wouldn't know how to prove, you know, like for one thing, right, you would first need a map that really goes from R to T rather than from R to T mod I. And that maybe one can eliminate it in very, very special cases. But I can't even say that for sure at the moment. Yeah, like somehow, like the method itself introduces, and yeah, you know, this degree shifting method is always up to some ambiguity of this form. So it's very hard to even get a map from R to T.
Any other question?
Earlier in your talk, you mentioned that the growth of the cohomology class in hyperbolic three manifolds is expected or proved in some cases to be exponential.
Right.
Can you see that in if you know R equals T in your diagram, that the number of them also grows in the Galois side?
I haven't thought about this, but again, I think so. This won't quite work for imaginary quadratic fields. So I guess, you know, you would have to, and that is the setting where L0 is 1. So I don't know what is known, say, for like L0 equals 2. I think like then it's not quite exponential. So I'm not sure because I'm not sure of how much we really are able to say now for imaginary quadratic. Although, I mean, it is a good question because maybe in the ordinary case you can really, so you could try, but we certainly haven't tried and I can't tell you off the top of my head if you will be able to see it.
Thank you.
Any other question? So if not, let me just give you a quick announcement. So next week, we will meet at 9 a.m. on Thursday. Jackson will speak. And also, I think he will speak at UCLA on Monday in different time zone. So if you can't make it, I mean, you can just give it a try. Okay, so let's thank Anna again.